All right, so I just wanted to finish up the lecture from Chapter 6, so after the exam we can move on to Chapter 7. There were just a couple slides left that I wanted to go over. Just reminding you, what we saw in lecture the other day was the idea that when we have an object moving in circular motion, we have a centripetal acceleration. And what we can do then is we can look at this from the point of view as of Newton's second law, where we replace with the acceleration the expression that we learned for centripetal acceleration. And so we're using F equals ma. And when we're doing this, these are forces that are going to be in the radial direction, or we could say along the radius of the circle. So it is in a way sort of breaking down the forces into components, but typically when we have circular motion, our two components are going to be radial, which is either going to go in towards the center of the circle or out away from the circle, and then tangential. So it's a little bit different than x and y, because as you can see, as we go around the circle, in this direction, right here, this is the radial, and then this is the tangential, but when we move over here, radial and tangential have changed sort of their orientations. So here's an example of where we might talk about a centripetal force. Remember, I wanted to emphasize in class that centripetal force isn't a force. There are forces that act as centripetal forces. So for example, we had talked about the case of a car going around in a circular path. This car is turning to the left, so it's kind of going around in a circle like this. And you guys talked about drift, which would be kind of like if the car would sort of tend to want to go this way. We need a force that keeps it in the circle. And we found that in this case, it would have to be the force of friction. We want it to be static friction, and at its maximum, the value of that force would be the coefficient of static friction times the normal force. So if we were looking at this particular problem, we want to find the centripetal force, which is going to be the frictional force. And so first of all, we might look at the forces in the y direction, because when we're talking about friction, sometimes we need to know the normal. So we could do normal minus mg is equal to 0. So the normal force is 900 times 9.8. So we know that. And that's going to be 8,820 newtons. Now, when we're looking at the forces, I'm just going to call it radial to emphasize that we're looking at a radial force. That's going to be our frictional force, which is mv squared over r. Now, actually, if I look at the information that I was given, while I know that the maximum static frictional force would be mu times the normal, I also noticed that because they said the frictional force is equal to mass times acceleration, I actually have enough information to actually calculate the right-hand side, which would actually allow me to solve for the frictional force in a different way. And I would find it was 1,125 newtons. In this problem, once I know that, just to remind you, we found that the force of static friction in the previous slide was found to be 1,125 newtons. We also found in the previous slide that the normal force was 8,820 newtons. If we want to find the minimum coefficient of static friction, basically it means what if the force of static friction is equal to the maximum value? Can we find this coefficient? So we just rearrange this to solve for it. And we find that the minimum coefficient of static friction we need is 0.128, which actually isn't too big. So it's good. That means we won't slip so easily. Okay. So this is a question I would have liked to do a demo of, but the question is, if you swing a bucket of water fast enough in a vertical circle, at the highest point the water does not spill out. And they're asking you if this is because an outward force balances the pull of gravity on the water. So in a sense, when they're talking about an outward force, they really are trying to trick you into talking about a centrifugal force, which is actually not real. It's a fictitious force. If we look at the bucket as it's upside down, as hard as it is to believe, you can make a bucket go around in a vertical circle without spilling out the water. You just have to have it go fast enough. What's working to your advantage is at the top, the water has a tangential velocity, tangent to the circular path. And so if it's upside down for a short enough period of time, the water's so busy moving in that horizontal direction that it doesn't have enough time to fall out of the bucket while the bucket is upside down. If we wanted to look at forces acting on the water, we would have the force of gravity, and we would also have the normal force that the bucket exerts on the water. So those two forces together would give us our centripetal acceleration times mass, so ma. If the water is falling, what happens in that case is the normal force goes to 0, because if the water is falling out of the bucket, then the bucket can't exert a force on the water anymore. And so at that case, mg is our only force, and we set this equal to centripetal force. And we can actually find the speed when that would happen. So if we go at that speed, at least that slow, the water's going to fall out of the bucket. We need to go faster than that in order for the water not to fall out of the bucket. Like I said, we don't want to talk about a centrifugal force because it's not a real force. What we mentioned in class is this is really a consequence of your inertia. It's the fact that your body wants to, if it's your body that, oops, I can't spell, inertia. It's your body that wants to keep going in its regular direction, and when you're forced to go in a circle, you feel sort of cut off from that motion, and you end up running into, say, the car door, the amusement park ride door, whatever, and that's why you feel like you're being pressed against it, but it's simply your inertia. And so we're going to, I want to move on to look at another problem. So here is a car. This is like a little play car and one of those little play tracks. The radius of the track is rather large at 5 meters, but in any case, the kids hit the jackpot with the toys. The mass of the car is 0.8 kilograms, and we're told the normal force on the car by the track at the top is 6 newtons, and then we want to find the normal force at the bottom. So the first thing we're going to do is look at the top, and we have identify our forces. We have a normal force, and we have gravity. So those are two forces acting on the car at the top. So we're looking at the top. And so we're looking at the forces in the radial direction, and that's mv squared over r. I'm just going to go with a typical down is negative, so I'm going to have minus n minus mg. And then I'm also have to put a negative sign on the right-hand side because the acceleration is also down at that location. And then you see I could just multiply through by a -1 to get rid of all these negative signs. That would be nice. And so basically, we're told that this car travels at a constant speed, and the information that they've given us will allow us to find V at the top, because it's going to be the same as the speed at the bottom, because I know the normal force is 6 newtons. And then I have the 0.8 kilograms times 9.8 equals 0.8 V squared over R. Sorry, R is 5 meters. So we can say V squared is equal to 6 plus 8 times 9.8, that's 0.8, sorry. And all that times 5 divided by 0.8. And then we take the square root of that to find V. And so we can say that V we found is 9.3 meters per second. So that's how fast this car is going as it goes around in a circle. And it's traveling at constant speed. So now we know V is 9.3 meters per second. And so we want to find the normal force at the bottom. So I'm going to identify the forces again. At the bottom here I have normal force. This time mg is in the opposite direction because it always acts down. So when I'm looking at the forces in the radial direction, I have normal minus mg equals mv squared over r. I've still used up as positive and down as negative. When we're at the bottom, the acceleration is up, so that's why it's positive. And so now I can find the normal force at the bottom is going to be mg plus mv squared over r. So it's 0.8 times 9.8 plus 0.8 times 9.3 squared over 5. And we find the normal force is 21.7 newtons. If you've gone on some like loop-the-loop ride, this should actually look kind of familiar to you, in that when you're upside down, because of the fact that you're going to start to fall out of the chair, you're not going to feel as big a normal force, but when you're at the bottom, you feel very heavy because your normal force is getting bigger. Okay, so, oh, that's weird. Did something weird to my picture. There actually should be a line going from here to here. So here is another problem. They're saying you have a pendulum and it has a mass swinging back and forth, and it says that at the bottom we have a certain value for the tension, and it wants to ask you to find the speed of the bob in order, knowing that. So we have, looking at forces again, we have tension in mg. And so if we look at the forces in the radial direction are going to be mv squared over r. So we're going to have tension is up minus the weight is equal to mv squared over r. And now we know what the tension is. It's 3/2 mg minus mg is equal to mv squared over r. R is equal to the length of the string, so we're going to substitute that eventually. On the left-hand side, when we get 3/2 mg minus mg, we get mg over 2, and that's equal to mv squared over L. The masses will cancel. You have g times L over 2 is equal to v squared, so v is the square root of gl over 2. And so we see, is this a choice? Yep, that's a choice, so it must be, the answer must be D. Okay, so here is again, it's a little bit of problems with the values getting messed up, moved around when it transferred to the video. So here we have something a little bit different. Here we have tension acting in the bob. This is what we call a conical pendulum because it's kind of going around, tracing out a cone with the string as it goes around in a circle. The circle is horizontal, would actually be perpendicular to this plane. We have mg acting down. And so in terms of our directions, what we would normally call our y direction is still vertical, but our x direction really could be considered radial because it goes into the center. So we want to figure out what the tension is, and so this angle right here would be beta as well, and I can look at my forces in the y direction, and those add up to be 0, and so I have tension times the cosine of beta minus mg equals 0. So T cosine beta is actually the vertical component of tension. I can rearrange this to find an expression for tension. And because the cosine of beta is going to be less than 1, that means that the tension is actually greater than mg. And so that's how I find my answer here for this particular problem. This actually, I didn't realize the problem that we did previously would be kind of similar to this one where we're calling this the friction, and then the friction is going to be the centripetal acceleration. So if we would say that frictional static force is mu s times the normal, we could find an expression for the speed of the car that it could go. Like the fastest it could go is whatever speed it would have when the frictional force is at its maximum. And this would be mg. So the masses will cancel out, and v squared is going to be mu s g times the radius, and so v is going to be the square root of that. Have that. And then I just want to take a look at the banked curve because this is this one situation where they kind of don't tilt the coordinate axes when you have the inclined plane, because the banked curve they're really treating as an inclined plane, but they're still keeping the y-axis and the x-axis in their normal orientation. And then pointing out that the normal force will have two components. N times the cosine of theta is the vertical component of the normal, and n times the sine of theta is going to be the x component, but which is also really the radial direction as well. And so basically what's happening in this case is that the n sine theta is going to be provide the force that acts as the centripetal force. And so if we look at that in terms of forces, so in the y direction we have 0, we have n cosine theta minus the weight is 0, so n cosine theta is equal to weight is equal to mg. In the radial direction we have n sine theta is equal to m v squared over r, and so what we're going to do is we're going to, from here, in this expression we can find the normal could be written as mg over the cosine of theta. We're going to take this and substitute it in here. So we write mg over the cosine of theta times the sine of theta equals mv squared over r. Masses cancel out. This can be written as g tangent theta is equal to v squared over r. And so basically we can find an expression for theta that's really in terms of the radius of the circle that we want to go in, the speed of the car. And so that can kind of make a relationship, like given a certain speed and a certain radius, this can tell us what kind of angle we would need in order to keep the car on the bank curve without any friction. So hopefully that helps and wraps up our chapter, and you can look at this after you're done studying.